This is chapter 11, video assignment number 1. So, in the text, we are given a body temperature of 37 degrees C and Henry's law constant, which is 3.8 times 10 to the negative 4 molar per atmosphere, and we are asked to calculate the molarity of blood that it is in contact with air at atmospheric pressure, and also the molarity of N2 in blood that is contact with air at 4 atmospheres. In order to do that, we are going to use one of Henry's law's equations. We are going to use the equation relating concentration with Henry's law constant and partial pressure of a gas. Plugging in 4 atmospheres gets you 4 times 3.8 times 10 to the negative 4 mole, with atmospheres canceling out and giving you molarity of 0.00152 molarity of N2 at 4 atmospheres. Plugging in 1 atmospheres gives you the molarity of 3.8 times 10 to the negative 4 molarity of N2 at 1 atmosphere. Now, since we are in molarity, we need to cancel out the liters and get it into moles. We need to get it into moles because we are going to be using the ideal gas law equation, which is PV equals nRT. This is because it relates all of the constants and values that we have while allowing us to get volume. So to get to moles, we have 0.00152 moles, molar times 5 liters. The liters on the molarity cancel out because molarity is moles per liter. That leaves you with 0.0076 moles of N2 for 4 atmospheres and 0.0019 moles of N2 at 1 atmosphere. Now, since we are ascending from 4 atmospheres to 1 atmospheres, we subtract those two numbers from each other to get 0.0057 moles of nitrogen lost when you ascend from 4 atmospheres to 1 atmospheres of pressure. Now, we can take that number and get our volume that is lost. In order to do that, we plug this into our PV equals nRT equation after we have solved for V algebraically, which equals V equals number of moles times the gas constant times temperature over P. Plugging in those values using the correct gas constant of 0.0821 because it is in the correct units of atmospheres per liter over moles of Kelvin. That cancels out the number of moles, the atmospheres, and the Kelvin to leave us in liters, which is volume. That gets us the second answer to our second question, which is 0.1451 liters of nitrogen gas lost when the deep sea diver rapidly ascends to the surface. Now, in order to solve for the amount of bubbles lost per liter, you need the volume of a sphere because we're assuming that a bubble is going to be a sphere. The volume of a sphere equation is 4/3 pi r cubed. We are given a 1 millimeter diameter of a bubble. We need the radius of that, so we divide it by 2. Then we plug that in, which gets us a volume of 0.5236 millimeters cubed. Now, in order to convert that to liters, you times it by 1,000 because there are 1,000 meters in a millimeter, and then there is 1,000 liters in 1 meter cubed. That gets us to 5.236 times 10 to the negative 7 liters. Now, in order to get that into bubbles lost, we need to divide 0.145 liters lost by the amount of bubbles, by the volume, of a sphere. That gets us 2.77 times 10 to the 5th total bubbles lost. That is the total amount of bubbles lost in 5 liters of blood when the diver rapidly ascends from 4 atmospheres to 1 atmosphere. In order to get that into bubbles per liter, we just divide that number by 5, which gets you 5,000 55,400 bubbles lost per liter of blood.